Okay, so Huy will continue telling us about these amazing techniques, combinatorial additive number theory.
Yeah, thanks, Avi, and thanks everyone for coming. Yeah, so today's talk is around Ramsey Cayley graphs and various related problems. And again, very soon you will see that this is just a continuation of yesterday's theme. So we will run into some additive combinatorics problem. And again, the perspective is we are going to tackle these problems with a flavor in additive combinatorics, but without groups. Okay. So again, joint work with David Cullen, Jacob Fox, and Liana Yepremian. So to start, let me, because part of the talk, many of the motivations in the talk is about Ramsey graphs. So let me first start by defining the classical notions from Ramsey theory. So for us today, we'll say that a graph G on big N vertices is C Ramsey if the largest clique and the largest independent set in G have size at most C times log base 2 of the number of vertices n. Okay, so in particular, we will say that a graph is Ramsey just to mean that there is some absolute constant C for which that graph or that family of graph is C Ramsey. So with this, let me just recall the classical theorem of Edish, one of the first applications of probabilistic combinatorics. And so he proved that there exist graphs on n vertices for arbitrary large n, which are 2 Ramseys. And I guess everyone knows how this goes, but let me just recall this argument of Edish that is by now a classic. So all that we need to do here is to actually consider a uniformly random graph on big N vertices. So out of all possible graphs on big N vertices, pick one uniformly at random. Or in other words, we just consider the Edish-Randy random graph. Gn 1/2. Okay, and after that, all that we need to do is to compute the first moment or the expected value of the number of cliques in G n 1/2 of size 2 log base 2 of n. And by linearity of expectation, this will reduce quickly to an explicit calculation. I'll not do the calculation here, but the outcome of this is that for n large, this is going to be very small. And in particular, just by symmetry here, the same calculation also works for the number of independent sets of size 2 times log base 2 of n. And so by combining these two, in particular, we now see that it's actually the case that most graphs on big N vertices do not have any clique or independent set of size 2 log base 2 of n. So in fact, most graphs on big N vertices are 2 Ramsey. Okay, so now for Edish-Randy random graph, we actually understand very well the distribution of large cliques or independent of the clique number or the independence number. Well, essentially, even if we replace this probability 1/2 by any parameter p. But in today's talk, we're not going to focus on Edish-Randy random graph. Instead, we will move to another example of random graph that is much harder to analyze because it is very structured, but it turns out that it has various interesting properties that I will tell you in a moment. So Okay, now let me tell you about the main object of today's talk, which is random Cayley graph. Okay. So again, let me fix the setup of this talk. So throughout the talk, we will think that we fix some finite, but otherwise arbitrary group G. So in particular, well, this group G that we work with doesn't have to be an abelian group. Now I'll define a Cayley graph given a symmetric subset F in G, and what I mean by symmetric is simply the condition that if an element little g is in S, then the inverse also has to lie in S. Now we can define a Cayley graph G of S, which is a Cayley graph in the group G with the generating set S. And this is going to be a graph which has vertex set just the group elements G. And the edges of this graph are going to be all of the pairs of group elements X, Y, for which X times Y inverse is an element in the generating set S. So we see that this symmetry condition on a subset S is simply just to ensure that this graph is going to be an undirected graph. So in particular, if XY inverse is in S, then YX inverse is also in S. Okay, so this defines a Cayley graph whenever we specify this generating set S. So now to define a random Cayley graph, I will simply specify a distribution of random generating set S. And so for us, given a parameter P in 0, 1, most of the time in this talk will be focused on P equals to 1/2. We can pick, so we can now define the following distribution on a random generating set S. So we choose each equivalence class, GG inverse, to be in S independently with probability P. And now this defines a random set S, and we will define the random Cayley graph with density P, which I will denote by G of P in this talk as the Cayley graph. G with this random generating set S. So now in particular, if P is equal to 1/2, then you can see that this random Cayley graph G 1/2 is simply a uniformly random Cayley graph on the group G. So out of all of the possible Cayley graphs of this form, we just pick one uniformly at random. That is what is G of 1/2. So in the talk, I will usually refer to a uniformly random Cayley graph. That simply means G of 1/2. Okay. So now here are our motivating questions. So let me pose here the two questions that will kind of guide us throughout this talk. The first question is, are uniformly random Cayley graphs Ramsey? In particular, does there exist some universal constant phi for which, say, over any reasonable group G, a uniformly random Cayley graph is C Ramsey? Now, in particular, we'll see later, depending on the answer, whether the answer is positive or negative, we can think about more refined questions. For example, can we say something, some characterization, some properties of the group that will allow us to understand more refined, in a more refined way when the uniformly random Cayley graph is going to be Ramsey or when it is not going to be Ramsey. So we'll return to various discussions around that in a bit. The second question is a conjecture of Alon. '89. And he conjectures that every group G every finite group G has a Ramsey Cayley graph. So this is just an existence question. And he conjectures that there must exist. Okay, so so more precisely, this means there is some universal constant C, so that over an arbitrary group, finite group G, we can find a Cayley graph of that group G, which is also C Ramsey. Okay, so we will very soon see that the answer to question 1 is going to be negative. So in particular, there are groups for which a uniformly random Cayley graph is not going to be Ramsey, and in which case it is quite interesting, okay, why or how we can approach Alon's conjecture, because with regards to Ramsey graphs, one of the best things that we can do so far is to take a uniformly random choice, a uniformly random graph, and yet when a uniformly random choice doesn't work now, what is a reason that we can still find the existence of some good Ramsey Cayley graph if the conjecture of Alon is true? So we'll return to that in a lot more details in just a little bit. So in terms of the structure of the talk, in the first part, I will tell you about various results on the first question, such as understanding Ramsey properties of uniformly random Cayley graphs in general groups. And after that, I will return to Alon's conjecture and see how we can make progress even when a uniformly random choice fails to be Ramsey. Okay?
You just care about abelian groups?
So, well, in most of the talk, when I discuss question 1, we'll work with arbitrary groups, so including non-abelian groups. And when we turn to...
But do you know the answer to these questions for abelian groups?
Do we know the answer to this question? It turns out to be negative already for abelian groups. We'll see in a bit. Yeah, and in fact, so we'll turn here. We'll see which kind of reason makes a group not Ramsey from the perspective of a uniformly random Cayley graph. Okay. Yeah, so just to say some motivations for why studying random Cayley graphs. From a Ramsey theoretic perspective, we know very little about exact values of Ramsey numbers, but it just happens that for all of the small values of Ramsey numbers that we know, the example turns out to be a Cayley graph, in fact, a Paley graph, which is a special case of Cayley graphs. And understanding Paley graph in general is a very challenging number theoretic question. So again, a random Cayley graph is itself kind of a useful probabilistic model for a Paley graph. And so understanding in a refined way random Cayley graph would hopefully give us more intuitions towards understanding these types of graphs, such as Paley graphs. A second reason is that, well, compared to Edish-Renyi random graphs, we know, for example, that it's it is quite easy to understand spectral properties of Cayley graphs and random Cayley graphs. And on the other hand, when we go to more sophisticated combinatorial properties that are not well predicted just by the spectrum of the graph, we know much less about these random Cayley graphs. So in some sense, we are staying with Ramsey properties for most of the talk today, and it's kind of an interesting test case for when, for the kind of properties that even if we know optimal spectral properties of these graphs, we still do not understand sufficiently well Ramsey properties. And this is our effort to understand better these types of properties without relying heavily on spectral properties. Okay? And of course, Cayley graphs appear many places in theoretical computer science and coding theory as well. Okay, so these are some quick motivations. Right. So with that, let me now go to discuss some of the previous results towards these questions. So let me just get all of the years correct. So the first result regarding the clique and independence number of random Cayley graphs is a theorem of Alon, which says that in an arbitrary group G, the uniformly random Cayley graph G1 has clique and independence number big O of log the size of G, big O of log the size of the group squared with high probability. So in particular, the clique and independence number is not very large, but it is a quadratic off from being a Ramsey graph. And this is the best result that we still know so far that works in an arbitrary group G without further assumptions on the group G.
But this is just an upper bound, right?
Yes, this is just an upper bound. Yeah, we'll get to the tight bound in a second. So this is a general upper bound that holds over an arbitrary group, and for non-abelian group, it's the best upper bound that we would know so far. Now there are many results that hold in special groups G, for example, abelian groups with a nice structure, and
So it makes sense to say just that Erdős's argument doesn't work in this setting because there is much less randomness to do that.
yes, exactly. So in a second, we'll try to write down Erdős argument in a random Cayley graph, and we'll see where it fails and what ingredients do we need to push this argument to work for a random Cayley graph. But yeah, the hardest challenge to analyze these graphs is because they have really little bits of randomness. It's just linear in the number of vertices instead of quadratic. Now, the next result that we know is from work of Ben Green, and he analyzed the clique and independence number of a uniformly random Cayley graph in two special classes of abelian groups. So in a cyclic group, Z mod n, he shows that G1 has clique and independence number big O of log n. So in particular, over the cyclic group Zn, a uniformly random Cayley graph is indeed Ramsey. And the other abelian group that he considers is the finite field vector space F2 to the D, which is the other perhaps nicer abelian group. And in this case, he shows that G1 actually has clique and independence number, not of order log n, but of order theta log n log n. Okay, so already in this group, F2 to the D, a uniformly random Cayley graph is not a Ramsey graph. So we see that the answer to this question is actually negative for one of the simplest group that we can consider, that's F2 to the D. Then with Robert Morris later, he shows that in Zn for n prime, actually, we can nail down the clique and independence number much more precisely. So G1 has clique and independence number 2 plus little o of 1 times log base 2 of n. So now in a prime cyclic group, we see that the uniformly random Cayley graph actually has clique and independence number matching that of the Erdős-Renyi random graph. Okay. And I'll mention the last result here is a result of Mrazovich from 2017. So what he showed here is just nailing down precisely the clique and independence number in G1 in F2 to the D. And turns out that we can get 1 point concentration of the clique and independence number for F2 to the D for most D. So in this case of F2 to the D, the graph is not going to be Ramsey, so they are going to be quite large, like asymptotically larger than log n size clique and independent set. But turns out that in a second, I will explain to you some intuition why this happened. It happens for a simple intuition. And that will also be the reason why we can nail down very precisely the clique and independence number over these finite field vector spaces, in particular F2 to the D. So I'll come back to the cliques and independent sets in F2 to the D in a little bit, and that will be important when we discuss our progress towards Alon's conjecture.
Concentration means that there is only one value. There is almost surely the size is one particular value.
Exactly. Yes, and
So do we know that Alon's conjecture is true for F2 to the D? Like that there is some Ramsey Cayley graph?
so that is a very interesting question. So we still don't know if Alon's conjecture is true for F2 to the D, and I'll get back later. As we think that is one of the most important cases to understand towards Alon's conjecture. The many groups other than F2 to the D fails to be Ramsey. So for example, if you take Fp to the D, let's say F5 to the D, it will also not be a Ramsey graph. We have an argument to fix the issue in all of these groups, but our argument only works over characteristic at least 5. So in some sense, the only cases, at least in abelian groups, that we don't know the answer is the case of F2 to the D and F3 to the D. So somehow these seems to be the hard cases. We'll see why when I give you the argument in just a little bit. Okay. So with that, let me now tell you about the first batch of main results in the talk. So these are results towards question 1. So with David, Jacob, and Liana, we proved that in an arbitrary group G, not necessarily abelian, G1 half has clique and independence number big O log n log n, where n is again the size of the group. So we improve the quadratic bound of Noga, and in fact show that this log n type bound, which we know is tight because of these finite field vector spaces, is actually the worst that can happen over an arbitrary group of order n. And so in particular, we see that perhaps the obstruction towards understanding Alon's conjecture is not really in the really complicated groups. It is actually in the groups that have way too many subgroups, and somehow it feels like the worst case is really groups that looks like vector spaces like F2 to the D. And in fact, with a much harder argument, pulling in a lot of the techniques that I covered in yesterday's talk with Jacob, we can prove in some sense that if a uniformly random Cayley graph fails to be Ramsey, then we can actually extract some structure of the group G that makes it look a lot like Fp to the D. So we show that if, so in now this is in an abelian group G, if G1 half has a typical clique number, let's say little n, which is omega of log G, then G must have at least exponentially in little n many subgroups. of size at both little n. Okay, so in some sense, if a graph and a uniformly random Cayley graph, sorry, if a group and a uniformly random Cayley graph in that group fail to be Ramsey, then there must be behind the scene a humongous number of subgroups of a specific small size lying in this group. And in fact, if you look at, let's say, f2 to the d, and you take little n to be log big N, log big N, where big N is 2 to the d, then you will see that this is actually the tight count for the number of subgroups, now subspaces, over f2 to the d of that specific size.
And that's the largest number of subgroups that any group can.
Yes.
I think F2 to the D is the one with the largest.
Yes. Right. So in some sense, it is just to point towards the intuition that f2 to the d should be the worst case. Yes.
Is that kind of an if and only if that if G has these many subgroups of
Yeah.
size n?
So we were hoping that we can get a characterization, and if and only if, turns out that it's not quite. So we can construct some weird cyclic group, maybe it's fp to the a times fq to the b. You tune none of the parameters in some appropriate way, and p and q are really on different scales, and we can construct something with many small subgroups, but still it is not Ramsey. So there's some failure of some second moment argument that happens there. So we don't quite have an exact characterization yet, but there's some indication. Yeah. And in some sense, we believe, it just by intuition, in a non-abelian group, it should be even harder for us to pack this many structures, this many subgroups into it. So it's really somehow should be the case that if we want to have really large clique and independence number in a Cayley graph, then the group has better look like f2 to the d. So, yeah. Oh, no, let me not. Okay. So let me now say, yeah, so as we see, this is log n log n. In general, we cannot improve it further. I'll remark later on what we can do to fix the uniformly random Cayley graph so that we can address Alon's conjecture. That's the second part of the talk. Okay, now let me just try to do the same thing that we did in an Eddy-Schwenyi random graph in this random Cayley graph example and see what happened. So we can do the first moment calculation. Okay, so this is going to be simple. We want to count the expected number, let's say of clique, of some size little n in this random Cayley graph G1/2. Well, again, by linearity of expectation, we can write this down explicitly. Just going to be the sum over all subset A of the group of size little n. Okay, so now it's 2 to the minus A inverse minus 1 over 2, roughly, times. Okay, I'll refine all of the quantities here in a second. No, the first one is going to be just this. So the observation here that we will use is that, well, in a group G, A is a clique in the Cayley graph GS if and only if A times A inverse or minus the identity element of the group is a subset of the generating set S. Okay, so more accurately, maybe let me put here this quantity S of A inverse. So here, little s of A inverse is the number of equivalence classes G inverse that are contained in the product set A inverse. And again, just to clarify the notation, A times A inverse is just our notation for the set of all elements of the form A times B inverse in the group, where A and B are elements of A. Okay, so this plays a role just like the usual subset on a different set. Okay, and it's just to be a bit careful with this, with how we compute this probability. So in particular, from this and from this, by our distribution of the random set S, we'll just get this exact formula out of the expectation calculation. So now, in particular, we can try to group these terms into some categories. So maybe we can sum over A in G, A of size N, sorry, not this anymore. We are going to sum over M, and what we sum inside is 2 to the minus M times NG and M, where now NG of NN is the number of subsets A and G, which has size little n, and for which essentially the product set has size little m. Okay, so it turns out that if we want to understand the expected value of the numbers of cliques in a random Cayley graph, then what we need to control is the number of subsets of the group for which essentially the product set A times A inverse has a small size. Okay, so this S of A times A inverse is up to a factor of 2, just the size of the product set A times A inverse. So in particular, this would reduce our main task to the following theorem, which is going to be the main technical theorem towards the upper bound on the clique and independence number. That is, in an arbitrary group G, the number of subsets A in G of size n, little n, with the product set A times A inverse have size at most k times n, so A has doubling at most k, roughly, is at most the size of G raised to the power some constant times k plus log little n times some constant times k raised to the power little n. Okay, so if you just plug in this upper bound on ng of nm, where m is corresponding now to big K times little n, then it's again an easy calculation to see that if we pick little n to be some constant times log n log n, then this is going to be very small. So I will not do that calculation here. Instead, let me make some remark about this result on counting subsets of a general group with a small product set. So turns out that all of these three terms that appear in this upper bound, so g to the k, g to the log n, and k to the n, they are all tight. So up to this constant big C, this is all of the terms here are needed in an upper bound on the count of such subsets. So let me just remark on why this is the case. So all three terms are tight. So to see that we need this term, the size of G raised to the power K, we can take, for example, we consider A, which is maybe just the union of some subgroup H of G together with some generic set of K group elements. Okay, if we take A to be such a set, it is easy to check that the doubling, the product set A times A inverse, is going to have size at most k times the size of A. So the size of the subgroup is about n. And furthermore, the number of such sets A is clearly at least big N to the k. These are just some k generic elements of the group. For the term G to the C log n, this is the more special term, and this is actually the term that caused the additional log n in the bound on the clique and the independence number. So this is not true in every group, but specifically if we take G to be Fp to the D, then we can just let A be even a subspace of order little n, and we can check that the number of such subspaces is going to be of order size of G to the constant times log n. Okay. Now, for the last term, well, here, what we can do is just to take a subset of size n of a subgroup of size bk times n. Okay. And the number of such subsets is order k raised to the n, and such subsets clearly also has doubling at most k. Okay. So this tells us that we need all of these three terms in theorem 3. Okay. And theorem 3 implies theorem 1, as I have remarked. So now there are several results in additive combinatorics using the containers method that works for nice groups like the abelian group G that allows us to count sets with small product sets. But actually, these results try to get an accurate count in some very different senses from what we are trying to do here. And those results don't work for subsets A of a group that have size little n that is really small compared to the size of the group. So for us, with this application to the Ramsey properties, we really need to have this count result being accurate for n that can go down to as small as log G, log of big N. And many of the counting results from an additive combinatorial angle would only work if the size of the size little n is quite a lot bigger than some power of log of big N. Okay, that's just a quick remark. So now the surprise, which is not because it's the same surprise as yesterday, is that this theorem 3, which is completely group theoretic, additive combinatorial, our proof of theorem 3 is again purely combinatorial. So we use almost none of the group structure apart from what I'm going to tell you now, which is essentially the same picture, the same combinatorial model for a group structure that we discussed yesterday. So let me just recall this combinatorial model for the group structure. So again, associate to each group G, we can consider, so for a group G, arbitrary group, we consider the edge coloring, an edge coloring on K of big N, where N is the order of G. So we can think that we are trying to edge color a complete graph where the vertex set is identified with the group elements G, just as in yesterday's talk, the color of the edge XY, in this case that we are looking at now for this version of the Cayley graph, is given by the equivalence class XY inverse, YX inverse. Okay, so this is an edge XY, and this is the color that we assign to this edge, which takes value corresponding to this equivalence class of elements in the group. Okay, so now we see that in particular, each color class in this coloring coming from the group is going to be either one regular or two regular. But in particular, each color class is going to have degree at most 2. So just as some examples, if we consider the group G being Z mod 5, Z mod 5Z, then the group elements look like 5 vertices of a cycle, and the color classes are going to be the 2 complementary 5 cycles that we have here. So we see that each color class in this case is 2 regular. And in the other case, we can consider the group G, the hypercube of 4 vertices. And in this case, we'll see that the color classes are just perfect matchings, so they are now 1 regular. Okay, so particular for each group, we can now associate to the group this combinatorial picture of the complete graph and some edge coloring on the complete graph that satisfy this combinatorial constraint. The maximum degree of each color class is at most 2. Okay. And turns out that this is sufficient for us to address this theorem 3. So let me take the more general result that holds over that combinatorial set. Okay. In fact, let me define the combinatorial generalization of a Cayley graph and random Cayley graph first. So make this definition. So we are given here an edge coloring of Kn, and we assume that each color class has max degree at most some parameter delta. Well, I'll usually call this delta bounded edge coloring. Now, we can define the analog of the Cayley graph in this combinatorial setting. So we saw that, okay, in this picture, what is a Cayley graph of the group? Well, a Cayley graph would just correspond to a union of some of the color classes. So we'll define this notion of an entangled graph to just correspond to exactly that. So an entangled graph is simply a union of some color classes. And now, similarly to the definition of a random Cayley graph over there is just a graph where it is the union of random color classes. We pick each color class independently with probability P. So here, random entangled graph and just let me overload the notation and call this also G of P is a union of color classes, each chosen independently with probability P. So this definition is made to mirror exactly what is the definition of a Cayley graph and a random Cayley graph when the coloring comes from a group. But in general, we can make, given an arbitrary edge coloring, we can make this definition of an entangled graph and random entangled graph. A random entangled graph, in some sense, shares the difficulty in our analysis of the Cayley graph in that compared to Eddish-Renyi, it is a highly dependent random graph ensemble, right? We call it entangled because whenever one edge of a color appears in the random graph GP, actually all of the other edges sharing the color with that edge also have to appear. That's why we call it entangled. In fact, I'm not going into detail right now, but there is a further generalization of this ensemble of random entangled graph, which we call delta independent graph. So a delta independent graph is just a distribution. So it's a random graph for which the appearance of an edge can only depend on a subgraph that have max degree delta. So this is kind of a representative case of that, but that is a slightly more general notion. All of our results go through for the delta independent random graph ensemble, and that addresses some questions, conjectures of Christofides and Marstrom on random Latin square graphs. Okay, but unless maybe at the end of the talk, if there's some interest, I can go into more details about these random graph ensembles. For now, I'll stay with the analysis of the entangled graph, which is already sufficient for us to analyze random k-depot. Okay, so let me state right over here the generalized version of theorem 3 to the combinatorial setup. So in the delta bounded edge coloring of Kn, the number of vertex subsets A of size n, and for which the number of colors appearing among the edges in the set A is at most k times little n, is at most the same bound we have over there. So big N raised to the power C, now that's the parameter delta, the max degree. And Ck becomes C times delta times K to the power little n. So we see that the size of the product set, or in fact, this notion of the number of equivalence classes that show up in the product set A times A inverse, this is exactly just the number of colors that appear in the vertex set A in the associated edge coloring to the group. So this corresponds exactly to this condition, and the count that we get here obviously correspond to the count that we claim in the group theoretic setup. Okay, so theorem 3 prime implies theorem 3 implies theorem 1, but furthermore, we can use again just the same first moment argument to see that theorem 3 prime would imply that in this more general delta bounded edge coloring setup, if we look at a random entangled graph, it will have clique and independence number at most, order log n log log n.
So one quick question. How necessary is the usage of Kn in the hypothesis of theorem 3 prime? Like, what if I had a different graph? Would there be a generalization of this theorem 3 prime?
What mean if you have a different graph?
As in, like, if I were not coloring the edges of a complete graph, but a different graph.
Yes, so it is not crucial that we have the complete graph, but you can work, for example, with a graph that is a sufficiently good edge expander, and the results would still go through in that setup. You will have now some dependence of these parameters on the expansion of the underlying graph. Okay, so the last remark that I will make here is that for our purposes, this parameter delta is actually not that important. We can use Weising's theorem to break each delta bounded color class into delta many matchings. And in particular, by changing this parameter k by a factor of up to delta, which is perfectly fine for us here, we can assume that we always work with a proper edge coloring, which is a one bounded edge coloring. Okay, so just a side remark. So later when I mention the proof and the ideas, I'll mostly work with edge coloring. Proper edge coloring instead of delta bounded edge coloring. Okay, so now let me tell you about the next key step to prove theorem 3 prime, and this brings back again, some memories from yesterday's talk. So we'll see again the appearance of the structured tree. So this is number 5. So main counting result, which is theorem 3 prime, we'll reduce it now to some structural result on finding structured tree in proper edge coloring. Okay, so this is going to be the main lemma. And this main lemma, this is the key technical ingredient. It is a quite immediate corollary of the same main combinatorial lemma that I mentioned in yesterday's talk. So in particular, later in today's talk, after I cover the main results, we will spend most of our time focusing on the sketch of the proof and the ideas behind the proof of the main combinatorial lemma yesterday, as well as the main lemma of today, which are closely related. So what is this main lemma? So in a proper edge coloring, now of k little n. So we are thinking that now we are forgetting about the environment, all of the remaining vertices in k of big N. We're just focusing on what the edge coloring is doing on this specific subset A of size little n. So now we have a proper edge coloring of k little n using a small number of colors. That's our hypothesis. Using at most k times little n many colors. And the conclusion, what we can find is that we can find a tree again on n over 2 vertices, very much like the combinatorial version of Feynman's theorem yesterday. The conclusion is slightly different now. So yesterday we said that we can find a tree using log base 2 of n plus some constant depending on k many colors. Now we can prove that we can find such a tree on n over 2 vertices using at most big O of k plus log n many colors. Okay, so the trade-off here compared to the combinatorial version of Feynman's theorem that I mentioned yesterday is just that we are no longer getting the correct constant in front of log n, but we trade that for the correct linear dependence on k. Okay, so turns out this is going to be very useful. In fact, let me state here also an easier version of this lemma. And in fact, this easier version is already sufficient to recover the log n upper bound on the clique and independence number, but it is not sufficient for some of the more precise results that I will mention, and it is not sufficient for the proof of Rouget's conjecture that I mentioned yesterday. So for that, we need the full strength of the idea. But I mentioned this because I'll give you a short proof in the next part of the talk of this easier version of the lemma. So the setup here is the same. We have a proper edge coloring of k little n using at most k times little n many colors. And what we can find is now we can find not just a tree on n over 2 vertices, a spanning tree. Okay, so the spanning tree on n vertices, and now it uses at most not k plus log n, but k times log n many colors. Okay, and we'll see in a bit why this is k times log n and what's the intuition for reducing it to k plus log n. It also happens that this is tight. So if you look to find a spanning tree, instead of 1 minus epsilon times n tree, you need to blow up the number of color from k plus log n to k times log n. So, okay, so these are the main technical lemmas. Now, let me say a few words. So the second part of the talk, our main goal is going to be ideas towards the proof of these lemmas. Let me now just mention how one can, very quickly, how one can use the conclusion of the lemma to conclude already the proof of this counting result. Okay, so it turns out that what is really useful here is that these trees are very useful as providing essentially a signature that allow us to count those sets A using that induced few colors in the edge coloring in an efficient way. Okay, so for example, for the simpler version, let's say that we can find in each set A a spanning tree that use a small number of colors. So the number of ways that we can choose the set of colors is not going to be large because there are so few colors involved here. And so in particular, this n to the k plus log n term just corresponds to the entropy or the number of ways that we can pick out k plus log n many colors. Once we pick out the colors, well, we can also essentially pick out the structure of the tree on n vertices. The number of trees on little n vertices is going to be just exponential in little n. So that is not a big factor to us here. Once we have picked out the colors and also the structure of the tree that we are looking at, we are essentially done. So let's say we have this specific tree, this specific colored tree that we use to encode the set A. If I just specify one element of the tree now, so let's say that we specify that this vertex maps to some specific vertex in Kn, because this is a proper edge coloring, there is at most one blue edge adjacent to the starting vertex. So that will fix this vertex, and we can just do that to decode the entire set A, given this colored structure and the starting vertex. So that is how we can count the number of these subsets determining few colors once we have the structured tree. Okay, so yeah, well,
This is in the case of full tree, and if you have only half of it.
yeah, so when you have only half of it, the situation is a bit more tricky. So if you want a tight rezone, then what we do is, okay, so when you have half of it, you can still determine half of the set A this way. So let's say we already pin down the locations of this subset A prime of size A over 2. Okay, now what we will do is as follows. For each of the remaining vertices of A, well, if this vertex introduce many new colors to the set A prime, in particular, if it introduce order n, many new colors to the set A prime, then I will just pay a cost of n to embed this vertex. The number of new color is going to go up by a factor of order n. The number of such vertices that we can embed is going to be at most order k. So this is just this term n to the k. After we do all of that, we are left in a situation where every single remaining vertex has, if we look at the colors that it produces when it talks to the guys that we have already determined, these colors overlap with many colors that have appeared inside. And it turns out that there's a simple double counting argument at that point to show that the pool of all available vertices in the graph that has this property is going to have at most order n or order kn. And so we can just like trivially count all of these, all of the ways that we can pick a subset from here to add to it at that point. But yeah, so there's some more details involved, but it's roughly the main idea. It's always the case that there's some cleanup that we have to do, quite similar to what we do here, both today and yesterday. But those cleanup are usually quite easy once we have this huge tree on a giant component of the graph. Okay, so are there any other questions? Okay, yeah, so instead of breaking right now, I think I would like to tell you also a little bit more about how we can go beyond uniformly random. Then we can take a break and return to the proof of these main combinatorial reasons underlying both today and yesterday's talk. So far, we have discussed the story for question 1 out of the 2 motivating questions. So we have discussed so far, okay, what can we say in most generality when we're just given an arbitrary group? Is it going to be Ramsey or not? And the answer is no, as we have seen. and we have some understanding for what is causing the answer to be no. So let me now discuss some progress towards Alon's conjecture. And so in particular, this is about how we can go beyond uniformly random. So, use this one.
For the factors in the bound, it seems that n to the log n is the most critical one.
Yes, in terms of causing you to be non-Ramsey,
Yeah.
and so the log n is exactly the factor. Right, so that is what we are going, that factor is what we are going to target now. So the point is that there are two competing terms here in the k plus log n. If k is already larger than log n, then we just don't have to worry about log n at all. So the case that we have to worry is, well, okay, something funny happens when k is smaller than log n. So that's what we would try to avoid when we go beyond uniformly random. So, okay, so I will just start with an observation. Why is the clique in number in f2 to the d or fp to the d in general of order log n log n? It turns out that you can show this quite easily that in fp to the d in the vector space with high probability, a uniformly random subset S, the generating set, is going to contain a subspace, let's say -0, for some subspace H of order log n log n. Again, n is p to the d, n is always the size of the group. So if it contains a subspace, then clearly there's going to be a clique, which is again any translate of that subspace. So this produces a clique. Let's say this gives a large clique, which you can take to be just H. And similarly, by symmetry, this produces the same large independent sets, which are just subspaces. So in some sense, they are abnormally large, but you understand very well what they are. And this is also why we can pin down precisely, because here we can pin down quite precisely using probabilistic arguments what is exactly the size of the largest subspace that is appearing in a random subset S. And that will dictate what is the clique and independence number in the corresponding random Cayley graph. So our goal is to remove these obstruction, which are subspaces, or in more generally, which are sets with really small doubling. Okay, so now I will tell you immediately what we can do to remove these obstructions.
So you first pick at random in S, and then you look at the bed subgroup. When you say remove, you mean what is removing?
Yeah, I'll tell you now. We cannot really pick it first and remove it, but this is what we can do, at least what works over most groups. So let's say over fp to the d, this is the modified random model. So for each x in fp to the d non-zero, we have a line determined by x. Okay, actually for simplicity, just for the sake of this talk, let's do it in f5 to the d. It's more explicit. So in each line, we have 4 elements, right? So this line the line would be 0, x, 2x, 3x, which is -2x, and then 4x, which is -x. We have to always pick an element that is inverse to be in the generating set, so we have no freedom there. what we will do here is we will pick exactly one of x minus x or 2x minus 2x to be in S, and the other pair to be in S complement. So we see that we introduce this correlation into our choice of the generating set, and it's very easy to see that now there's no subspace that lies within S. Whenever we have an element x in S, 2x is not going to be in S. So immediately we destroy all of the subspaces. Okay, so this key property of S, which is very simple, is that if x is in S, then 2x is not in S. But now, one small thing is that subspaces are not all of the sets with small doubling in this abelian group. So we have all of the other things that look approximately like a subspace as well. So we need to show that they don't appear. They also don't appear. They therefore cannot appear as a clique in the Cayley graph once we pick S according to this model. So now I can state this as a small lemma. So if we take S satisfying this key property star, and if A is a clique in GS, in a Cayley graph with generating set S, where G is F5 to the D, then A cannot have more small doubling. Or in an abelian group, so I'll write minus. A minus A is at least A to the 4th. Okay, so immediately, for any set A that has a chance to be a clique in this random Cayley graph, when we pick according to the modified model, the parameter K cannot be very small. It must in fact be at least little n to the 1/3, way bigger than log n. So immediately we can ignore the log n term. So once you have this combined with theorem 3 prime and the first moment calculation, you can show that now the clique number of a graph sampled from this model is no longer log n log n, it's big O of log n. Okay. So I'll give a very quick proof of this lemma. It's a quite the cute argument. So what we observe is as follows. If A is a clique in S, well, because of this property star, A has no solution to a certain linear equation. Okay, this just comes directly from the fact that A is a clique, and S satisfies this property that if X is in S, then 2X cannot be in S. So there cannot be any solution to this. We can rewrite this equation in a nicer way.
You mean with the all different AI?
Yes, no non-trivial solution. Yeah, so with all different AIs. We can write this equation equivalently in this very symmetric form. And now, because it's symmetric, it is much easier to show that if A has a too small doubling, then it must have some solution to that equation. Okay, let me write down the argument now. So what we do is we say that because of this property, because there's no solution to this, if we look at the set A plus the dilation of A by a factor of 2, so this is, we just take each element of A and multiply 2 to it, then we sum that with A. This is the collection of all elements of the form A plus 2B. These are all distinct because there's no non-trivial solution here. So in particular, this will have size equal to the size of A squared. But at the same time, there are results in additive combinatorics that give us upper bound on this sum of dilates. It's one of the questions that has been studied, but here I will just use a pretty much trivial bound. So this is clearly a subset of A plus A plus A. And now the Plunker-Ruger inequality, another classical result in combinatorics, would allow us to bound the iterated sum sets in terms of the doubling of a set A. So in particular here, I'll just write that the bound gives is something that looks like this. So A plus A plus A is at most the doubling, which is a ratio A minus A over A to the power 3. That's how many terms here. And then we multiply by the size of the set A. So if we just combine these two equations, then we'll immediately obtain that the size of A minus A is at least A to the 4th. Okay. So this is an argument that works in F5 to the D. Turns out that you can write a similar arguments that work over more general groups as well. So let me now summarize all of the results that we can obtain following this kind of direction. So the first result that we can prove towards Alon's conjecture is that for most n, most integers n, any abelian group of order n admits a Ramsey Cayley graph. Okay, so this to address Alon's conjecture for most abelian group. Now there's nothing mysterious about most n here.
Don't forget the powers.
I cannot get the result if n, let's say, is dominated by powers of 2 or powers of 3. Other than that, anything else works. Yeah, so we see if we are working in characteristic 2, it's a disaster to try to enforce this kind of scenario. So something is interesting there. In fact, there are Ramsey theoretic results that tell us that in F2 to the D, if we take an arbitrary coloring, as D grows very large, we must also have arbitrarily large, almost monochromatic subspaces. So in some sense, we cannot simply hope to band subspaces based on this kind of modification. We must do something more sophisticated. And we think that is a very interesting question. Now, let me mention also that under this model, we can analyze actually very precisely the clique and independence number. So that's the second result here. If we look at Fp to the D, so for P, let's say, equals to 1 mod 4. If we look under this modified model, in the modified model, this random Cayley graph produced by this model, the random Cayley graph is going to have this nice property, is self-complementary. I will explain why I'm saying this. With clique and independence number, actually 2 plus little of 1 log base 2 of ligand. And in fact, in this result, we are working over G, which is Fp to the D. We do not require P to be small. So P can be an arbitrary prime as 1 mod 4. In particular, G can be just a cyclic group, Zp. And in this modified model, we have a very simple proof to show that actually the clique and independence number is accurately 2 times log base 2 of n. Now, we mentioned a self-complementary graph is just a graph that's isomorphic to its complement. This, I'm putting this result here because in a work on dual source coding, so zero error communication, by Alon and Orlitsky, and which is the dual source coding task is also connected to some communication complexity kind of question. They were motivated to look for a graph that is a Cayley graph, that is Ramsey, and that is self-complementary. Okay. Maybe I won't go into the details of why that is needed, So they ask if there exists a self-complementary Ramsey Cayley graph, and this in particular address in a strong sense the question of Alon and Orlitsky. And we just mentioned in words that we can also show more general versions of these results. So for example, the last theorem maybe that I will write down is, let me just put it here, hopefully it's fine, that in fp to the d so let's fix some integers are bigger than s, and then in fp to the d for p, let's say bigger than 2r, we can prove that there are Cayley graphs. Oh, sorry. So we can find Cayley R colorings such that the clique number of any union of S color classes is 2 plus 0 of 1 log based R over S of n, where n is p to the d. Okay, so it's just kind of a multicolor generalization of what we discussed for Ramsey Cayley graph. So a Cayley R coloring is, it just means that we specify a generating, we partition the elements of the group G into generating sets. There are R generating sets corresponding to R colors. And we can, when we consider the corresponding decomposition of the complete graph into the R color classes corresponding to each Cayley graph. And this shows that we can match the behavior of the random construction for this question on minimizing the clique number of the union of any number of color classes as long as we don't use all of the colors. Okay, so now the last word before perhaps we take a 5-minute break. The result here, where we just want a Ramsey Cayley graph, we just try to generalize this argument over more general abelian groups. As I say, as long as we don't get stuck with small characteristic, it all goes through nicely. For this result, where we pin down precisely the asymptotic constant, it turns out that the main tool here, okay, pinning down this constant corresponds to pinning down the constant in front of k in this result. So if we want to get the correct constant for the clique number, we must get something like this, but with the constant in front of k being the correct constant. And turns out that we have it over vector spaces because we can get the correct constant in front of k by connecting it to the Freiman-Rogers theorem over vector spaces, which over vector spaces, we already know from the result of Evans, O'Hara, and Lovett, there's a precise constant, there's a very precise bound on the Freiman-Rogers problem in these groups. Okay, there's a little bit more still, so that's why it works very nicely over vector spaces, but we have to think more carefully when we go to more general abelian groups. But it's just quite amusing that this is actually, again, connecting back to the Freiman-Rogers circle of problems. Okay, so I'll take some questions now, and maybe we can take a 5-minute break before we go back to our main combinatorial lemmas.
So do you know anything about non-abelian groups?
Yeah, so now we can try to do something like this in a non-abelian group. Here, we needed to do some reordering to get from this somewhat arbitrary equation to a nicely symmetric equation. This reordering doesn't work in a non-abelian group. Now, there's still something that you can do in a non-abelian group. We can still push through a modified model like this in an arbitrary non-abelian group. We get that A has no solution to a certain equation that don't look as nice as this, but there's a way to, so there are two ways to proceed. One can use the approximate group mechanism of Pruitt, Green, and Tao to show that in this model, the clique number is little o of log n log log n. So it's not log n, but it is separated away from the maximum log n log n. And we believe that we can also make that a little bit more quantitative by using sub-results of Sanders and a lot more work, but we won't be able to quite get a good bound out of that. We can just separate it away from the upper bound. Yeah.
This intuition that these vector spaces are the worst case, do you think that's kind of important for this combinatorial paradigm to be successful?
Okay, so right, so one could say that the combinatorial paradigm is very general, so it is capturing in particular all of the vector space case within itself. Well, if we just work with the generic combinatorial paradigm, then I agree that it seems like we need something more intriguing to move beyond vector spaces. But I think that, you know, once you have some additional assumption about a group or some additional assumption about the model that you are working with, you would get additional inputs that may go into the combinatorial paradigm. So in that case, we may still hope that we can see some improvement already within the combinatorial paradigm that, you know, allow us to get better answers. Yeah, we just need something that separate ourselves from the vector space setting. Of course, another thing that can happen is that this combinatorial paradigm may produce to us some structures that is like pushing us a long way, but then at some point we may just bring back the group structure like we did yesterday, and then that allows us to get the conclusion that we want. So for example, in this result that I mentioned, that we get this characterization, it actually works like that, which is why there's a word abelian in the hypothesis. So we use what the combinatorial structures that we have produced by the main lemma, and then we refine it until some stage that we get something sufficiently clean that we can just pass back and use some easier input in the group theoretic setup that allow us to conclude. So yeah, there are various ways to do things here, and the combinatorial perspective may not by itself go the whole way, but it can certainly get us a lot of mileage, and then we can combine it with other things that we know. Yeah.
Just one question slash comment slash, so there is this, like we have this paper on rainbow cycles that kind of has very similar flavor of various bits and pieces floating around.
Yes.
So if I remember correctly, like what we are proved, like what the rainbow cycles imply is a version of theorem 3 where we will give you a control on the dimension of A, a
Yes.
certain version of dimension of A. Which if you, not quite what is in the paper, but slightly tweaked, you can get also, if you have a small dimension, you don't have that many sets. You will get like a weaker upper bound on the, like, than what you're getting there, not quite as precise, which I think would still translate to some improvement over the Noga, just not quite directly.
Yeah.
So, I mean, the question really here is what, like, do you get something out if you have in theorem 3 some more information, like you don't just have control over the counts, but you actually know that your A needs to be contained in a kind of, in a subspace, but now it's the Freiman dimension, it's a different type of dimension. So, and different spanning plus minus 1 dissociated or over integers. Anyway, so general question is just, if you have more information about A in theorem 3, I tell you it's a set of small dimension, is that useful for something somewhere, what you're doing?
So
Just the counts.
So, okay, so for the version of theorem 3 that I wrote here, I mean, we just proceed combinatorially that directly there. So I don't see immediately a way to combine that information. I believe that there are various things where it's helpful to look at, to inject additive information at various places, and that may be helpful, right? I don't know if that's getting at the question.
Yeah, I mean, it's a very general kind of fishing in the dark question.
Right. So in particular, I can tell you that something that goes on here, for example, for this theorem sharpening, essentially what happens in theorem 3 is that in some cases, you can use some sort of structure to say that, oh, maybe I'm not counting A in the ambient that is in the entire group, but now we are counting A in some host that is now much smaller than the group. Maybe this is along the line of what you say, you know that, oh, A must actually have dimension much smaller than the dimension of the ambient group. So I can just instead count A in this much smaller subgroup that have small dimension. And that would allow us to improve various terms that come up here. So for example, instead of g to the k, you have the ambient raised to the k. So that is one of the main steps that go behind the proof of that theorem as well. So certainly, yeah, something like that can be helpful in various places.
I mean, yeah, our result is kind of like, it's a sparse setting, it's weaker than what you're getting, so it would not give you anything of the like stronger flavor like that. It was more kind of, but precisely what you're saying makes a lot of sense.
Yeah, so if there's some analog Combinatorial results in various settings, and it would certainly be useful. Yeah, so as I said before, and we'll encounter this in just 5 minutes, I believe you may get something that goes to the direction of this easier version. So maybe, so here we really care about the k dependence, but up there, is it k plus log n or is it k times log n is not important for the log n log n upper bound result. It's more important for all of the subsequent results that I discussed. But
Just with our thing, you'll get the log n in the exponent there as well, which I think just
I see.
to something extra also.
I see, maybe a small extra thing.
So it would be the log squared, but it would not kind of go to your.
Okay, I see.
Good more, so we take the break now. Yeah.
Yeah, so now I will show you a quick proof of this easier version of the lemma, and then we'll work towards the proof of the lemma. So this is proof of easier lemma. Okay, so for this one, what we will do is the following. So let's start from an arbitrary vertex v of the graph. So the picture looks like this. In every step, we'll just try to grow as large as possible in a greedy way, a component around this vertex v. Okay, so maybe now let's see not the component that we start with is just this single vertex v. Now in step I, for I is 1, we will just pick a color, we call it Si, such that the color Si, the edges with color Si grow the component Ci minus 1 to a component Ci, and we just choose this color greedily so that the size of Ci minus the size of Ci minus 1 is maximized. Right, so the process may look very simple. So in the first step, we may just choose any edge that connects the vertex v to some other vertex. So now we have the component C1, and then in this step, we'll try to pick some color so that the edges with that color will extend this component C1 as much as possible. So in this case, there are 2 edges of color yellow adjacent to the vertices in C1. We pick the color yellow, and then we have now the component C2, and we just continue to do this greedy process. Okay, so what is going to happen here? Let's say we are at step I. So in particular, we have some component Ci minus 1. Well, the number of colors, so let me recall that when I write n of Ci minus 1 and Ci minus 1 complement, this is just the set of colors that go between a vertex in Ci minus 1 and vertex outside Ci minus 1. Well, okay, so first, the number of edges between Ci minus 1 and Ci minus 1 complement is obviously Ci minus 1, n minus Ci minus 1, right? And now, because there are k times n many colors in total in the entire graph, the number of colors between Ci minus 1 and Ci minus 1 complement must be, because we have at most, k times n many colors, what we can conclude is that there exists one color that is adjacent, one color that produces at least Ci minus 1, n minus Ci minus 1 over k times n, many edges between Ci minus 1 and its complement. Okay, so pick one such color, and now if we pick this color, then the guarantee that we have is that Ci is going to be at least, well, Ci minus 1 plus this quantity here, okay, so here we can just perhaps rearrange this slightly. So in this, maybe in this form, it is more transparent. Why? We can finish the argument. So if we write n minus Ci, we can upperbound it by n minus Ci minus 1 times 1 minus Ci over Kn.
Yeah, I would say I might.
Oh, Ci minus 1. Okay. Okay, so let's imagine what is going to happen here. In the first, okay, so it will take us, okay, so in the first k times, we are going to take, okay, so we will do this for some big O of k times log n many steps, right? So, okay, so we can see that n minus Ci is roughly decaying exponentially with the rate given by, since we're the size of the component over Kn, we can just do a rough calculation to see how many steps it would take for the size of the component, let's say, to increase by a factor of 2. And if we just combine all of that, there's a simple calculation to see that k times log n many steps would suffice for us to make n minus Ci decrease all the way to 0. Okay, so it's just a quick sketch of why k times log n many steps would suffice for us to collect all of the vertices to be in the component. And once all of the vertices are in the component, then clearly there's a spanning tree that uses only this many colors. Now, there's a construction that tells us that this is actually tight if you want the spanning tree. So just spend a second to say what it will look like. So the construction will look like this. You can take some set of vertices S of size maybe root Kn. The edge coloring will try to put all distinct colors inside this small block of size little s. So here we have roughly n vertices left because S is going to be very small. And what we do is essentially, so in between this big block and the small block, we'll put a random coloring using k times n many colors. And we have to be a little bit careful in making sure that the random coloring actually behaves like a proper edge coloring. And after that, we can check that under this random coloring, there's a simple probabilistic argument to tell us that below k times log n many colors, we cannot have enough color to connect this big block to the entire set of little s many vertices. Okay. So it's a construction showing that for a spanning tree, k times log n is necessary. So with that, let me proceed to, okay, the most interesting part, which is the tight main lemma over there, which, as I mentioned before, is important for our corollaries in additive combinatorics that I mentioned yesterday. So in particular, the combinatorial version of Feynman's theorem and Rouget's conjecture, and important for some of the results I discussed before too. Okay, so now we'll discuss the proof of the lemma. So it turns out that the way that we will prove this lemma is roughly in two steps, where the first step is the statement that I gave you yesterday as the main combinatorial lemma. So let me just repeat that. I tend to call this, maybe let's call this the robust lemma. Okay, so the output of this step, again, we have the same setup. We have edge coloring on Kn using Kn colors. What we want to produce is we can find a set S of big O of K many colors. And so that if we look at the edges with color in the set S, at least n/2 vertices are in components that satisfies the nice expansion property that for all vertex subset A prime of size at least, let's say, omega n, so any little delta times n, the number of colors between C and A prime is omega of Kn. Okay, so this is just rewriting the main combinatorial lemma that I stated in yesterday's talk. Let's see that this lemma would quickly imply the main lemma that we have over there. So okay, so what is the picture that we have? We have these components. By the way, we should think that these components are roughly like random set of vertices of size k. We'll see in a bit why that's what we should think about these components of size roughly k. So let's say we have about n/k of these components that we have found using this robust lemma. And they have the property that, well, whenever we pick one component and we take any large subset of vertices, the number of colors between this component and the set of vertices is a constant fraction of the total number of available colors. Now, what we can do is we just pick a random color in each step. Well, this guarantee tells us that each component is adjacent to an edge of this color. To another component. With pretty good probability, with probability omega 1, where omega 1 means an absolute constant independent of k. That means that if we keep track of the random variable x, which is the number of these components that we have, once we expose a random color, the expected number of components goes down by 1 minus omega 1 by a constant factor. So in at most log n many steps, we'll be able to merge all of these components to one big component of size n/2, and this gives us the lemma. Okay.
Now, maintain the property that you also maintain the property that the new components have the property that you want.
Yes, but this is actually quite easy to maintain, right? So the point is,
Because they each have this individually.
that's right. So if we have even more of them in one big component, it's great. I can ignore all of them except for one. So it still works. Yes. Okay, so now I will give you some ideas towards the main part now, which is this robust version of the lemma. Okay. So what we will do is the following. This is our process for proving this robust lemma. We will pick order k random colors. Say S1, S2, up to S order k. Okay, now we actually fix a vertex. So we do this kind of analysis, kind of vertex by vertex, and then we conclude by some application of Markov inequality. So let's get there, but first I fix a vertex V. And we'll analyze some event about components that we can grow from the perspective of this vertex V using this sequence of random colors. Okay, well, and what we will do is the following. We will keep track of certain sets Ci, which again, just these are sets that we grow around the vertex V. The set Ci will have this property that it has size exactly I. And the next property is that if we look at the vertex Vi, which is Ci minus 1, so here again C naught is just a set V. We look at the vertex Vi, which is in the difference of Ci and Ci minus 1, then we can guarantee that the color set around Vi is essentially disjoint from the color set of all previous vertices that we see in Ci minus 1. So we write it, and then I'll explain in words. Okay, so again, N of V is the set of colors of the edges adjacent to the vertex V. This is saying that if we look at the colors that are adjacent to Vi, but it was not adjacent to any of the earlier vertices that we discovered, and this is essentially close to N. So essentially, these are all new colors that we discover once we add the vertex Vi into the set Ci. Okay, so this property, let me call this set of vertices good. So let G I be the set of such Vi, such vertices Vi. Okay, so now the point of our analysis is as follows. Well, technically, once you give me the sequence of colors, this breaks the graph into a bunch of connected components. There's some component there that contains the vertex V. It turns out that it is quite hard to do the analysis from a global perspective like that. So instead, we will grow in a very controlled way these kind of controlled components Ci, which is actually not the largest component that we can collect using these colors, but somehow that is very useful for the analysis. So now I will tell you how we grow these components Ci, in particular, how we choose the vertex Vi. Okay, so what happened is that given Ci minus 1, let's say this is V1 all the way up to Vi minus 1. Well, this determines the set Gi.
Is GI the set of it's not the set of VI, right? It's the set of neighbors of
Yeah, so for GI, I will call it this. So it's the set of vertices that let's call it V, such that it satisfies this constraint here. So it's like one of the potential choices we could pick so that this holds, right? Is this okay? Yeah. Yeah, so this is just to say I'm going to pick VI from this pool of vertices GI. So, but given Ci minus one, GI only depends on Ci minus one, so we know what are the vertices in GI. A simple double counting shows that GI is large. So essentially, almost all vertices are still contained, a large number of vertices are still contained in this available pool of vertices GI. Now, I'm going to specify the choice of VI. So what we do is we pick the smallest time Ti such that STI connects Ci minus one to a vertex Vi in this available pool GI. So that is how we define the vertex Vi. Okay, so now what is funny of this is a quite natural definition, but what is funny about it, this is roughly how the component is being determined. So we start with the vertex V, and then we have the time step. So at each time, we are going to sample a color, S1, S2, and so on. Well, first, when we start from V, we have this pool of vertices G that are good for us. We are going to wait and wait until we hit some colors, let's say S4, that connect V to a good vertex V1 in this pool G. After that, we essentially restart again. We don't only look forward after we discover V1. Perhaps it is the case that there is an earlier time that connects where a color S2 was sampled that connects the vertex V1 to a new vertex V2 in the good pool of vertices at this step. And then we would just continue like this. So perhaps now we go to the future and we discovered the vertex V3. But after that, we may go back and find the vertex V4 and so on and so forth. So in some sense, as we grow this component or this set Ci, we keep going forward in time, and sometimes we go backwards in time, which in particular means that in the proof, we have to be very careful. Because let's say I already condition on what the component Ci minus one looks like. So I condition on the sequence of vertices V1 up to Vi minus one and the colors that determine these vertices, because that would imply some information about the colors that have been sampled up until the time that we see the last vertex in this component Ci minus one. But now, let's say I want to understand some event that happens and cause me to fail to find the next vertex V5 in a not too long time wait. That would require me to understand the conditional distribution of the colors that are sampled at the earlier time steps, given that somehow this is the component that is realized at this point. Okay, so somehow this is why the probabilistic analysis of this proof is fairly tricky, but this is our process for discovering the robust component that has the property in this robust lemma. Maybe just the last thing I would just say, what is the intuition behind this process? Successfully discovering a component of size at least order k using at most order k many colors. So what happens is that just for intuition, okay, so or actually let me write down that our goal is to prove the following main claim behind the proof. So the claim is that, let's say that it takes time big T. So maybe we sample many colors. We just wait until we find something that we want. Let's say that it takes time big T for this process to build a component, to build a set Cj, where J is of order omega k. So with the guarantees that we have throughout this process, once we find a component of size omega k, we will automatically satisfy the property that we want in this robust lemma, this property on the number of colors. So our goal is to find a component of order k using as few colors as possible. That means in a time that is as fast as possible. So the key claim is that the probability that T is bigger than alpha k, this is going to be exponentially decaying in this, let's say, number alpha. So in particular, if we take like some huge constant times k here, that means with high probability, we are going to be able to successfully find the component that we want. Now, the last thing I will say behind why this estimate is true is that, well, let's say that we condition on Ci minus 1 and the relevant information that allow us to find Ci minus 1. Let's assume that even after this conditioning, the colors that are not involved in the process are somehow still just uniformly and independently distributed over the pool of all available colors. Just for simplicity for this intuition. So what happened is that actually the probability, the number of colors adjacent to Ci minus 1 is going to be quite large. So the number between Ci minus 1 and Ci minus 1 complement, or in fact, even the number of colors between Ci minus 1 and this good pool of vertices Gi, this is going to be essentially 1 minus delta times n times I minus 1. So this tells us that, well, essentially, as long as in the past and in the future, whenever we see a color in this huge set of colors of size not n, but n times I, we'll be able to succeed and grow the component Ci minus 1 to the component Ci. So as the component grows larger and larger, it is easier and easier for us to find a color that grows it, up until the time that it is of order k. So that's when this argument no longer holds true, but that's when we want to stop as well. Okay, so this is just to say if, yeah, so because as the components grow, the number of colors going out of the component also grow. This means that the probability that we fail to connect Ci minus 1 to Gi by time, let's say big T, this is going to be significantly smaller. So this is going to be essentially at most exponential in minus Ni over Kn times T. So we expect that the components grow faster and faster as its size is growing until it hits size omega k, and which is why in omega k in big O of k many steps, we will be able to successfully find a component of size omega k.
What is the rate of change of the GIs in this process?
What is the?
How the sizes of the GI change in this process?
Yeah, so the GI will get slightly smaller because this set of colors we exclude is growing and growing. But that is why, as long as I is not too big compared to k, let's say I is like some epsilon times k, the size of GI we can still guarantee to be very large. It's close to all of the vertices.
All of them?
Yeah.
All of them?
Yes. Right. So that will surely break once the component, when I is large compared to k, but when it's very small compared to k, and it's a simple argument to show that most vertices are good in this sense. Almost all.
Okay, this,
Question?
okay, thank you. First one.
I don't think I really understood the intuition for why you have to choose the TIs in this way.
Yeah, so it turns out that, okay, so there are various things that can happen. So maybe to say, well, why don't we just keep our life simpler by only going forward and never look at the color that we have bypassed in the past? Well, let's do the rough calculation. Well, at first we have only n colors and there are a total of kn colors. You have to wait at least about k steps for this vertex V to make a connection using one of the colors adjacent to it. So this is about time k that we get to see the vertex V1. After this, these two vertices combined have about 2n many colors. Out of k times n many colors, we will need to wait a time about k over 2 until we see the next vertex V2. If we keep doing this, the argument will at best produce that we can see a component of size omega k in times k plus k over 2 plus k over 3 plus k over 4, blah, blah, blah. And that's going to be about k log k. Okay, so there's a way to make that argument potentially go through if you are willing to have a suboptimal dependence on k in the result. But just for the optimal dependence on k, somehow this is the analysis that we had to take. There are various, before this, we tried to do various things. So for example, we can try to, like another picture that one can think is not to just do the analysis locally from the perspective of each vertex. We can try to say that, okay, maybe up to time k is not that, let's say up to time some constant times k, most of the components are already growing sufficiently well. And in some sufficiently short time, many of them will actually double in size because they combine like this. And once they combine like that, like in a way that's well distributed throughout the graph, then of course the next time we need for some pair of them to connect is going to be decreasing by a factor of half. So this will get us like some exponential, like some geometric sequence which will sum up to order k. But it seems actually very challenging to push through an analysis in a global scale like this in our sampling procedure somehow. Things are really not concentrated and things are not well distributed. So most of the time we have to push through this argument assuming no concentration at all, and that's one of the just technical difficulties here.
Oh, more quick, yeah.
What are the main places where the argument changes if you have an expander and?
Yeah, so for example, if you look at this argument, you can see that it's very easy to see that it holds in an expander because the only thing we used was that, in a complete graph, we have many edges between C and C complement. Now in an expander, as long as you have sufficiently many edges, then you have some version of this that would just go through equally well. And
But the number of colors is a bit weird. I guess I did not understand. In an expander graph of degree D.
if you're talking about really sparse expander graph, then the quantitative dependence may depend on various things here. So when I was thinking of an expander graph, it's going to be maybe a dense expander graph that has a sufficiently good edge expansion parameter gamma or something like that. It will have some potentially bad dependence on gamma, but it may work better if you have a dense graph. But in terms of quantitative aspects, I'll have to check. So if you go really sparse, it may be different. Yeah, so something similar goes on in this argument. Most of the time we only have some set of vertices, which is a component, and some other set of vertices, which is this good set that we want to connect to. As long as there is sufficient connection between these two set of vertices, then we can push the argument through. So we just need this kind of well-connectedness or expansion between essentially a small set and a large set.
Maybe I missed it, but is there a kind of chance to combine the main and the easier lemma? Because each has slight Like, so, or maybe I missed whether the n/2 is tight in the main version of, like, or can you hopefully connect everything maybe with k?
No, I said it's impossible.
Yeah, so if you want everything, you cannot do better than k times log n, so that it was.
With what, k being,
Yeah. But of course, if you don't like n/2, any 1 minus delta times n, there's some big old delta of k plus log n.
Okay, thank you very much.